Dr. Steve. Yes, thank you, Alex. Our guest today is Dr. Stephen Furlanetto. He's from University of California, Los Angeles. He got his PhD in 2003 from Harvard. He did postdoc at Caltech. He was an assistant professor at Yale, and then he landed the UCLA job and is now a full professor there. He's got a book called First Galaxies with Avi Loeb. You might want to check that one out. He's won the Helen B. Warner Prize from the AAS and the Packard Fellowship, and those are early career awards. Super happy you're here with us, and we're going to learn about early galaxy formation. And thank you so much for being here. And we'll just chime in if we have questions. Is that all right?
That sounds great. Yes.
Okay. Fantastic.
All right. Well, thank you for having me. It's a pleasure to talk to you. Wish I could be there in person, as I said. So today I'm going to be focusing on the first generations of galaxies to form in the universe and how we have tried to learn about them over the past couple of decades. So to set the stage, I want to talk about how that era fits into what we do understand. So this is a timeline of the history of the universe with the Big Bang at the left, going to the present day at the right. So that's about 14 billion years of history. And one of the questions that drives cosmologists, and especially me, is trying to understand how we get from the very simple universe following the Big Bang to the complex structures that we see around us today. And that began by Hubble basically identifying galaxies in the 1920s, and then a long period of trying to understand what their properties were. We now know that galaxies today are pretty well defined. They fall into two major categories, ellipticals and spirals, with just a few outliers. They follow well-defined scaling relations, and they interact only rarely and are growing slowly. So you can think of today's universe as the mature era of galaxies. One of the, sorry?
Just, I laugh.
Oh, okay. Good. Yeah, over the past 30 years or so, with big telescopes and new technology, we've tried to push farther and farther back to look at earlier generations of galaxies. And one of the key things you have to understand when we do that is what's called the cosmological redshift, right? So the universe is expanding since the Big Bang, and that basically means that all the distances in it are expanding, including the wavelength of light, right? So if galaxy emits a photon, and that travels, 10 billion years to get to us, all that way that it's traveling, its wavelength is getting longer and longer. And so because blue light then becomes red, we call that redshifting. So a slightly more quantitative version of what this looks like is, imagine that you have a galaxy and you're taking its spectrum. The black is the intrinsic spectrum of this galaxy. And so as those photons travel toward us, they're all going to go to longer and longer wavelengths. And so you can basically use the amount of redshifting that has happened over the photon's trajectory as a proxy for how long this light has been traveling. And so as astronomers, we use redshifts as a proxy for time. So the bigger the redshift, the longer ago the galaxy emitted its light. So I will be going kind of back and forth between those, but I'll try to stick to times as best I can. Okay, so this is an example of looking for the most distant galaxies that we can. It's called, actually, this is the Hubble Ultra Deep Field. So the Hubble telescope stared at a basically empty patch of sky for hundreds of hours to look at the faintest objects that it could, try to find these distant things. And so almost everything that you see in this little image is a galaxy. The blue galaxies are mostly the ones that are close by, and then the redder the object gets, that's the more and more distant galaxy. So with that, as of 5 years ago, we had been able to study galaxies up to about a billion, or back to about 1 billion years after the Big Bang. So that's almost 12 billion years of cosmic history. And the galaxies that we found, sorry?
We're good.
Okay.
Hopefully there's no interference, but we're fine.
Okay, great. So the galaxies that we saw, the most important thing about them is that they're smaller, and the farther back in time you get, the smaller they get, right? So galaxies are growing up over time. They're also interacting with each other more violently. But the galaxies that we're seeing are also kind of built of the same constituents that we're seeing. We're not seeing any like weird kinds of stars or anything like that. So I think of these last 10 billion years or so as the angry teenage years of galaxies. The key thing to keep in mind going forward is this idea that galaxies are getting bigger over time, right? So we refer to that as hierarchical galaxy formation. The growth occurs in a couple of ways. All right, this diagram shows that we start out with these small objects that then merge together into bigger ones. All right, but a large chunk of the growth is actually just occurring kind of as material steadily falls onto the galaxies. This is showing the history of star formation in our universe. Okay, so on the right side of this diagram is early times, and on the left is late times. And then the y-axis is showing the density of star formation in the universe, right? And so if you look at early times, stars were being formed only slowly, right? But that ramped up quickly over the course of a few billion years until about 10 billion years ago. We refer to this peak in the star formation rate density of the universe as cosmic noon, right? When the action was strongest. And that rise over early times reflects this idea of hierarchical galaxy formation, of things getting bigger over time. However, all right, you'll see that in the past 10 billion years or so, okay, that has not been happening. The star formation has slowed down in the universe. That is not because hierarchical galaxy formation turned off. It's because other things start going on, all right? And one of those important things is supermassive black holes. Sorry, this cosmic time diagram, ignore that. That's on the wrong slide. So we now know that at the center of almost every galaxy, there is a supermassive black hole, millions or billions of times more massive than the sun. We believe that those black holes grew through accretion, so matter falling onto them and being swallowed up. While the matter is infalling, all right, it is accelerated to high velocities. It collides with each other and heats up, and that hot, dense matter then emits light. All right, so we see the matter accreting onto these supermassive black holes in objects that we call quasars, some of the most luminous objects in the history of the universe. And it turns out that the density of these quasars also peaks at around the same time of the universe's history as this peak in star formation, okay, this cosmic noon. So this is showing the density of quasars of various luminosities. Each of the sets of curves is a different luminosity. They all peak about 10 billion years ago at the same time as this cosmic noon, all right? And we don't think this is a coincidence. We think that these black holes get big and bright enough that they're actually able to stop star formation on big galaxies around this time. Okay, that's a process called quenching. And so even though these black holes are actually only a tiny fraction of their galaxy's mass, they're able to have a big influence on how they're forming stars. One of the pieces of evidence for that is that if you look at in the nearby universe, all right, you can compare the masses of the black holes inside galaxies to the masses of the galaxies they live in, right? And so that's what this plot is showing. Each of these points is a nearby black hole inside of a galaxy. And the line is the overall trend in them. So the black hole mass, it turns out, is roughly proportional to the stellar mass of the galaxy it lives in. It's 0.03%, right? So it is, sorry, actually, it should be 0.3%, I believe. But it is, so it is small, all right? But as I said, they nevertheless can have a big impact on the galaxies they live in. Okay, so we've gone back to galaxies about a billion years after the Big Bang. That was as far as the Hubble telescope could take us. So to study the earlier universe, we had to use other techniques. One of the most important is called the cosmic microwave background. So the cosmic microwave background is the relic radiation of the Big Bang, all right? And it turns out that it last scattered about 400,000 years after the Big Bang, and then would basically travel freely to us since then. So if you take an image of this cosmic microwave background, it's basically a baby picture of the universe. It's the earliest image that we could capture of the universe. This is an example from the Planck telescope. right? And what you're seeing is, imagine like the whole sky, you like cut a slice through it and you unfold it, all right? That's this. So this is an all sky image of this background. And it's seeing the temperature of this particular radiation. Uh, Importantly, all right, although there are these red and blue spots which correspond to hot and cold, the colors here are very exaggerated. So at this time, 400,000 years after the Big Bang, the difference between the hot and cold spots is about is about 1 part in 10 to the 4. All right. So it's a very, very almost uniform, simple universe at this time. We're just seeing these tiny fluctuations begin to grow. Now, it's important for our story, okay, not because there are galaxies now, there aren't, right? So it's not a baby picture of galaxies, but these fluctuations are basically the DNA out of which the galaxies can eventually grow. And so we're seeing kind of the initial conditions from which we expect to grow into galaxies. Now, what is missing, right, are the birth and the childhood, the tumultuous childhood of these early galaxies that get you to kind of the almost mature, angry teenage years of galaxy formation. And that is this era that we're trying to fill in now. This era is divided into 2 pieces. The dark ages refer to the time after the cosmic microwave background was last scattered until the first stars form and start to light up the universe. And once that happens, we call it cosmic dawn, right? So the dividing line here is when the very first stars in the universe formed. Now, we have never seen these first stars, but we expect that they actually are quite different than the normal stars in the Milky Way and other nearby galaxies, because it turns out they have to form through an entirely different mechanism relying on molecular hydrogen. I'm not going to have much to say about them in this talk, although observing them is sort of the holy grail of what we're after when I discuss this era. So it's something we're all aiming toward, but we don't think we've gotten there yet. All right. So that begins the cosmic dawn. The end of the cosmic dawn is something called reionization. So when the cosmic microwave background last scattered, that happened because the universe cooled enough for atoms to form. The protons and electrons recombined to form hydrogen. Hydrogen remained neutral until you got these first luminous sources. And once you do that, then those stars or black holes or whatever they are can make ionizing photons. And some of the ionizing photons leak out from the galaxies around them and make little ionized bubbles. And so this is a computer simulation of how these ionized bubbles form. They're the blue regions. The black is the material that is still neutral. And as the first galaxies grow and merge in this hierarchical galaxy formation picture, so do the ionized bubbles around them, and they eventually fill the universe. And that's what we refer to as reionization. So the universe goes from neutral back to being ionized. There are some measurements that suggest that this happened about, or ended at least about 1 billion years after the Big Bang. All right. And from kind of a conceptual level, this reionization is very important because at this time, only a few percent of the matter in the universe was actually inside of galaxies. So it took the photons that are produced by those galaxies to affect the other 95%. So at this reionization moment, all of the kind of normal matter in the universe had been affected by stars and galaxies and black holes, even if they weren't directly incorporated into them. Okay, so that's some context. The big thing that has happened in the last 5 years is JWST, the James Webb Space Telescope, all right, which launched on Christmas Day, 2021. I was briefly transported to my childhood when I woke up and immediately wanted to check my phone, or check something in my phone now, presence in the past, that the launch had been successful. So it's a large near and mid-infrared telescope. It's the mirror, which is this gold thing here, is 6.5 meters across. It has about 5 times the collecting area of the Hubble Space Telescope, so it's exquisitely sensitive. And one of the chief reasons that observes in the infrared is that cosmological redshift that I mentioned. So if we are looking at these first galaxies, their light has been redshifted by a factor of about 10, 6 to 10. And so what was originally ultraviolet is now in the infrared. What is originally optical is now in the mid-infrared. And so this was one of the big goals, was to try to study these distant galaxies, right? And so what I want to talk about today is give you some context on how we think the physics of galaxies might work, right? And how the recent observations by JWST have challenged the simple models and sort of I joke with my students that we haven't actually learned anything from JWST. That's not really true. We haven't solved anything, but we've opened up a whole slew of new questions. And so that's what I really want to focus on for a lot of this talk. Okay, so we will begin with just a simple model of galaxy formation. And I say simple, that is not because I'm dumbing it down. The kind of theoretical astrophysics I do, I try to focus on starting simple and then building in complexity as needed. And so you'll kind of see how that informs what we understand of these JWST galaxies. Okay, so the simplest thing that we can kind of measure about the galaxy population is how many of them there are. And the way we parameterize that as astronomers is with what's called a luminosity function. So we're measuring the number density of galaxies just as a function of their luminosity. Astronomers use strange units for this. So in the plot I'm showing here, luminosity increases to the left on the figure. All right. The different colors are at different stages during the early history of the universe. Okay, so the red is at redshift 8. That's about 700 million years after the Big Bang. And then the up to blue is redshift 4, which is kind of up into those angry teenage years of galaxies. And so what's happening over this period is that the number of galaxies is increasing, and that's just a reflection of this hierarchical galaxy formation picture, okay, that as time goes on, we get bigger and more things. So can we understand how many we are seeing? Right, well, let's start with this simple model. So we think that galaxies form inside of gravitationally bound clumps of dark matter called halos, right? So that's kind of the setting. And the gravity of this massive dark matter halo is going to pull in nearby gas. And the fundamental job of a galaxy is to turn that incoming gas into stars, right? So we turn some fraction of the gas into stars. Immediately, almost immediately, once that happens, things get complicated, right? Because stars produce high energy photons, which then stream back out through the gas that's coming in. Massive stars, when they end their lives, run out of fuel and can't support themselves and explode in events called supernovae. And those supernovae are extraordinarily energetic. They dump a whole lot of energy into the gas. And they give it so much energy that they can actually drive it back out. Okay. So you can think of galaxy formation as on this, very, very simplest level as essentially a one parameter model where the thing you need to know is per unit star formation, how much energy are you dumping back into the fuel, the gas, through these feedback effects, supernovae or whatever else you want to appeal to, okay? So that makes it sound simple. It's not, because all of these feedback effects and these really energetic explosions are very hard to model from first principles, okay? But what we can do is basically say, well, we understand that this feedback picture can explain a lot of the features of nearby galaxies pretty well, okay? And so if we take the same kind of feedback models that work nearby and apply them to the early history, does that work? Is the first question. All right, so here is an example of how a galaxy grows in this very simple picture. So now time is going from left to right here, okay? The bottom panel is showing the mass of different components. The dotted line is the mass of the dark matter clump, the halo in which the galaxy is growing, right? And then the solid black line is, given some amount of feedback, how the stellar mass of this galaxy is growing, okay? So they're both growing kind of smoothly and exponentially. On the top panel, I'm showing the fraction of the matter, the normal matter, that the galaxy, the halo has, that is converted into stars. And so you can see in this simple picture, it's I've fixed the feedback strength to give you like 5% of the mass is turned into stars. If I crank up the feedback efficiency, what that means is there's more energy acting back on this fuel supply for each star that I form, right? Then I'm going to need fewer stars to drive out the gas that's coming in. And so I will end up with less of a stellar mass or a lower stellar mass, right? Okay, so we have some idea of how to normalize this feedback, again, based on how this works in local galaxies. And it turns out that if you take those kind of reasonable estimates, it can explain these luminosity functions of early galaxies too, right? So here now, this is the same kind of thing you saw before, except now luminosity increases to the right. The points are the data, the observations of how many galaxies there are at this early time. And then the curves are different flavors of this feedback-based model, okay? So basically it worked fine, all right? There's no indication that these galaxies are particularly weird in any way. But, all right, on the other hand, we do know that galaxies are a lot more complicated than just forming stars out of incoming gas, all right? And the first thing that an astronomer would think to do is say the gas that's coming in doesn't directly form stars. Instead, it forms like a reservoir of gas called the interstellar medium. And then from that interstellar medium, a bunch of magic happens and stars form, okay? So now we're going to add in a second parameter to our models, which basically describes how efficiently can you turn the gas in the interstellar medium into these stars. Right. Once the stars form, they're still going to exert the feedback. Now that's going to act on this interstellar medium and push it out, right, and halt future star formation. But now we do have two parameters. Okay, so what happens in this picture? All right, well, this is the same kind of growth of the galaxy, okay? Dark matter halo growth is the dotted line. The thick black line is the stellar mass, all right? It's growing in almost the same way as before. The thin black line is the amount of gas that's hanging around in that interstellar medium reservoir ready to form stars, okay? And so I've chosen parameters here so that those two pieces, the thick black and the thin black line, have roughly the same mass, okay? Now, if I crank up the efficiency with which the interstellar medium... Question?
Nope, I think our chairs are squeaky.
Oh, okay. Sorry. Okay, so if I crank up the efficiency with which stars form, right, then you get the blue curves, okay? And the interesting thing that happens is it does not change the stellar mass essentially at all, okay? The same amount of stars form, and that's because the star formation is still controlled by the feedback, because that is regulating how much stuff is able to come in. What this parameter changes instead of the stars is how much gas is left in the galaxy, this thin line down here. Okay, if I have more efficient star formation, I need less that gas hanging around in order to form the correct number of stars. Okay, so what this is reinforcing is if we're studying the number of galaxies, we're learning about how this feedback process is working. Now, I said a bunch of magic happens and we form stars. Okay, it's actually quite complicated magic. So maybe this conclusion is just an artifact of not treating star formation properly. So we can do this better, all right? If we look at how the stars actually form, we start off with this gas reservoir, the interstellar medium. The first step is we have to form very dense clouds that can actually make stars. And that requires gravitational fragmentation, right? So you form those clouds. In the clouds, the star formation process happens. And then shortly after the stars form, we get that same feedback that we talked about before. Now the feedback, though, plays a dual role, all right? It's going to be kicking gas back out of the galaxy, but some of the energy is going to be left in the ISM and stir it up, all right? So we've got these explosions going off, and it's going to move the gas around and stir it up, cause turbulence, basically. And the cool thing about that is that turbulence is going to regulate, is going to resist how the gravitational fragmentation, this first step, happens. Okay, so as you form more stars, you stir up the interstellar medium and you slow down future star formation. So it turns out that nearby galaxies enter kind of this equilibrium state where they're forming just enough stars to stir up the interstellar medium just enough to like have a slow and steady rate of star formation. Okay, so we don't really understand in detail how this cycle works, but it doesn't matter, it turns out. So if you take several different models of this cycle and you replace that one parameter with these more complicated models, the same thing happens. It turns out the feedback is still what's controlling how many galaxies that we have at early times. So again, no indication that something weird is happening. All right, so do we understand early galaxy formation? Sort of, in the sense that, like, at least as of 5 years ago, we had simple models that seemed to work fine. And then we could take those simple models and extrapolate them to even earlier times that we couldn't see with Hubble, or smaller galaxies that were too faint to see with Hubble, right? And kind of get baseline expectations. On the other hand, these kind of simple models also help see, like, oh, all the things that could have gone wrong that maybe we should also be worrying about. And this is a partial list. All right, I will be returning to a few of these later on when I talk about the JWST results. I will particularly highlight, I've listed black holes here. I told you how they are super important in understanding star formation at later times. Haven't even mentioned them at all yet, right? So that's obviously something that can happen. Another one that's important and seems really minor are timescales, okay? So this cycle that I just mentioned of kind of an equilibrium where the feedback from the supernovae is just supporting you enough to get this slow and steady star formation, right? Well, you have to establish this cycle in the first place, okay? And that's a question of timescales. In particular, there's a delay between when the stars form and when you get your supernovae, because you have to wait for the most massive stars to live through their lives and then explode. That takes of order 10 million years, all right, for massive stars. That has to establish itself, all right, before you get another generation of stars, okay? And what the timescale that limits you in forming stars is this first step, gravitational fragmentation to form your cold clouds. It turns out that happens on about the free fall time or the orbital time of galaxies. In the Milky Way, that orbital time is 200 million years, all right? So you form a generation of clouds, they form some stars, feedback kicks in. All of that happens in roughly 10 million years, right? Long before you're going to form your next generation of stars, of clouds and head stars. But if we go to the cosmic dawn, all right, then the time scale for this cloud formation is only about 5 million years. All right, so now instead we form our first generation of clouds and stars. And then while we're waiting for the supernovae to go off, we have time for a whole other cycle of star formation, okay? And so this equilibrium gets broken, and that has pretty dramatic effects, right? And this illustrates that. So this is, again, just following a galaxy, a single galaxy forward in time, right? The y-axis now is the rate at which it is forming stars. The thin line is the rate that happens if you are able to establish that equilibrium, okay? So it's the same kind of model I was showing you earlier. But by simply adding the delay to the supernovae, okay, I get the thick black line. And what happens is while you're waiting for those first supernovae, you form a lot more stars than you otherwise should be able to. And then once the supernovae go off, you have so many extra supernovae that it just blows out all of the gas in your system, and you're not able to accrete matter and hence form stars for some period until the supernovae end. And then accretion begins again, and you go through this cycle again and again, okay? The interesting thing that happens here is how this affects, or what parameters affect the history of this galaxy. So if you recall, that star formation efficiency parameter didn't matter as long as you can establish the equilibrium. But in the case now, it does very much matter because it's telling you how many stars you can form in the time you have before the supernovae kick in. All right. And so if I crank up that efficiency, I get the blue curve, which goes through many more and much stronger cycles of these bursts. Okay. And so now this second parameter all of a sudden does become important by kind of what I thought would be a sort of innocuous change to the system. Okay. Now we're going to see burstiness pop up soon. This delay is giving us these star bursts, these bursts of star formation. And it must happen, okay, but there are other reasons why burstiness can happen too and give you similar kinds of effects. All right, last thing before I move on to JWST is, remember that reionization event when the ionizing photons from early galaxies leaked out and reionized all the hydrogen in the universe? Okay, that is this big phase transition that we are trying to understand. With these simple galaxy models, we can kind of make a baseline prediction of how that should be progressing because we know how many galaxies we have and how many ionizing photons they're producing, and so can kind of follow this in time. So this black line is the kind of history that you got from our simple galaxy models, okay? So reionization would end at a redshift of 6, which is about 1 billion years after the Big Bang. All these different green points are astrophysical measurements of when reionization is going on. I guess I should say this, the y-axis here is the fraction of the universe that's neutral as opposed to ionized, right? So it's going from mostly neutral at early times to ionized at late times. And these measurements are showing it's happening roughly 1 billion years after. So this looked good, okay? There was one kind of concern that some of us, including myself, had, which was actually we don't maybe quite have enough galaxies around to finish reionization. And so there might be a problem getting things done early enough. Right? You could push things so it was okay, but it was sort of a concern. Okay, so now JWST is launched in 2021, late 2021. So we've had a few years of its observations, and it has opened up a ton of questions challenging this very simple picture that I just explained. All right. So as I alluded to, like this studying early galaxies was one of the prime motivators of JWST and its design. Sorry, there's another stray cosmic time here. Ignore that, please. So there have been a bunch of different surveys looking for these early galaxies, and these are showing like patches of the sky of different ones of these. And there's a tension we have, like given a limited amount of time you can use to observe, you can either look at a big patch of sky, but look at each piece for only a relatively short amount of time. That's like this orange big patch here. Or you can stare at a small patch of sky for a very long time to look for the faintest possible things. And that's this black one up here. So there's been a range of surveys to try to get these objects. And through them, we now have thousands of high redshift galaxies. Okay, so this is a histogram showing how many galaxies we found at different redshifts. So the cosmic dawn starts at like redshift of 6. So everything on sort of the left 2/3 of this plot is in the cosmic dawn. And we've got the top dotted gray line. That's sort of the sum of all these different surveys. We've got like tens of thousands of sources, right, in this cosmic dawn now. There are also other surveys that have focused on spectroscopy. So taking spectra of these galaxies, that's much more informative, but also takes a much longer time. And so we have spectra of, maybe a few hundred galaxies right now, as opposed to, 10,000 that we can see, we can identify. Remember that idea of hierarchical galaxy formation, that over time we get more and bigger things. Okay, you can see that this histogram more or less follows that expectation. Okay, except at the very, very earliest times, there seems to be a flattening and even a bump. Okay, ignore that. It's because it's actually very hard to figure out what these really faint things are. And so a lot of that is actually going to be interlopers or objects that are actually at much later times masquerading as these early things. Okay, so what have we learned? All right, well, I'm going to list a few of the things that have surprised me, and I think most people. I'm not going to give any answers as to what these surprises mean, because that's still in progress if we're trying to figure it out, but I will give you some hypotheses for them at least. Okay, so the very first thing that was noticed within, literally days of the first surveys being published, is that there are too many luminous, very distant galaxies, okay? So if you recall, I showed that plot that showed our simple galaxy form models were working fine, all right? This is taking that and now same kinds of tests, but adding in the new JWST data, right? So each of the panels here is showing a luminosity function at different times. So the upper left panel is the end of cosmic dawn and then going progressively earlier through the rest. The points are the observations from these early surveys, and the curves are the same kind of simple galaxy models I described. And you want to compare the points to the lines with the same color, okay? So up to redshift of 10, so that's 600 million years after the Big Bang, things are working fine. The data and the models line up pretty well. But beyond that, the data were showing more galaxies than our models predicted. And so the cyan dashed curve, that is the redshift 10 model repeated at earlier times. And you can see that that provides a better fit, okay, in many ways than the models at the right times. So the number of galaxies is kind of flattening out, right, rather than decreasing like we expected. So to some extent, that's this contamination problem that I just mentioned. But even after a lot of hard work in the past couple of years, this problem has persisted, okay? So there are too many bright things. There are lots of potential explanations. I will be talking about most of these potential ones over the next few minutes. All right. To give you an idea of the problem, okay, the scale of the problem. So here I've taken more recent data, and the top panel are showing luminosity functions at 2 different times, okay? The left panel is kind of right when the problem is kicking in. The right panel is an even earlier time. And again, the points are the observations, and the solid curves are our predictions from the simple model. The bottom panel is trying to show like what violence do you have to do to our galaxy models in order to resolve this. Okay, so it is saying, suppose that you increase the luminosity by some factor. How much do you have to increase the luminosity? The gold curves are saying, let's take all of our galaxies and just bump up their luminosity. So at redshift, or at redshift 11, okay, just when this problem is kicking in, the gold curves show that you need to increase the luminosity by 20, 30%. There are tons of astrophysical things I can imagine that change things on the order of 20%, so not a big deal, all right, but something to address. If we go to this earlier time, all right, then the problem becomes worse. So you need to basically triple the luminosity of each galaxy in order to make it work. Okay, so becoming more severe at earlier times. All right, the first solution would be to just say, okay, maybe these parameters for how many stars you're able to form that I was calibrating to teenage and mature galaxies are just underestimates, and that these galaxies at early times are able to form more stars than we expected. Okay. So in that case, I would take my expected luminosity function, this black curve, and I would just shift everything to the right. Okay, so I'd take my already luminous galaxy and I'd make it a few times more luminous. I'd take my faint galaxy, I'd also make it a few times more luminous. All right. So I'm pushing everything to the right. In this case, okay, I have a prediction that these most massive things that used to be bright are still the brightest, right? They're just even brighter than I would have expected. Okay, that's one surprise. And we'll get back to it because it's connected to everything else too. The second surprise turned out to be that star formation at these earlier times was way more stochastic than we had expected, right? So this is a spectrum of a galaxy. I think this is about 800. This galaxy is about 800 million years after the Big Bang. All right, and if you're not an astronomer, this probably doesn't mean a lot to you, but basically the stuff in the ultraviolet to the left, right, that's produced by very young stars mostly. But this feature, this bump that happens at about 0.4 microns, okay, that is characteristic of relatively an older stellar population. And so what turns out to work best for this galaxy is that this galaxy stopped forming stars about 50 million years ago, 30 to 50 million years ago. And only then, only if you had killed off those very short-lived stars would you be able to see this bump right here. All right, so this galaxy, most of the galaxies that I showed you, at least in the equilibrium case, right, were growing steadily. All right, and this galaxy is not doing that. It is stopping forming stars. There are many other galaxies that show signatures of very rapid, very recent star formation. All right, and so star formation is varying a lot more strongly than we had expected. Okay, and again, there are lots of reasons that can happen. One of them is that delayed feedback that I just mentioned, that I mentioned a few minutes ago. All right, but there are other reasons like the galaxies themselves, right? The star formation is driven by gas falling into them. Maybe you're just getting a big clump of gas come in, or maybe, you haven't had gas come in for a while. So there are lots of reasons why this kind of star formation history can happen, but it's happening at levels that we did not anticipate. This, though, can actually help resolve this question of why are there too many bright galaxies, okay? So what is happening in this case then is that if every galaxy that I expect to have some size, some luminosity, actually has a range. Maybe it's happens to be forming stars very rapidly at some point, or maybe it is slowed down forming stars, right? So I'm adding in some kind of distribution around this underlying luminosity function. That is going to push the observed luminosity function to have more luminous things. And the reason is because I have many more kind of medium-sized galaxies that can upscatter to bright luminosities than I have intrinsically bright galaxies that will downscatter to be faint. All right, because I have many more medium-sized things than big things, I end up getting a boost because of this burstiness to the observed luminosity function. Okay. Interestingly, though, this is going to change the nature of what these bright objects actually are. All right. So in this picture, most of the bright objects are medium-sized things that happen to be caught at the right time to be luminous. All right. And so most of the luminous things that we're looking at are not in the most massive dark matter clumps. All right. They're kind of average. And so if we can measure that mass, right, then we can start to distinguish these. These are the kinds of tests that people are now doing, all right, but we're only now starting to explore these questions that in new ways. Okay, the third surprise is that there are too many of these supermassive black holes at early times, okay? And there are a variety of ways in which these have been found. So this GNZ11 is a very luminous, it's actually the first redshift 10 galaxy to be found by Hubble. And if you take a spectrum of it, it has these weird lines that require very, very high energy radiation that you wouldn't get from stars. So it's probably a result of a black hole at the center. Other distant galaxies have been found with X-rays, and others have been these things called little red dots, which are basically this kind of mysterious population that is quite common, and that we don't really know what they are, but most people think that they are also powered by black holes. Now, not only are there lots of these black holes, but they're big. Okay, so remember that in the local universe, black holes are the mass of a black hole scales with the mass of the galaxy it lives in. Okay, so the relation between stellar mass and black hole mass locally is shown by the purple line here. All right. When people go and measure the masses of the black holes that we're seeing in these early galaxies, all right, they pop up in these green points. Okay, they're big error bars, there's uncertainties, but the average relation of these early galaxies is that the black holes are much more massive than the local relation. They're about 70 times more massive than we had expected. Okay, and this is a big caveat. They're big systematics, so these could just be wrong. Okay, but assuming they're correct, it poses a really fascinating puzzle. Let's suppose that this relationship is true, okay? That every galaxy has a black hole that is following this red line. Well, I can go out and I can measure the density of stellar mass density of galaxies in the universe, even at these early times, right? And then I just have to multiply by this factor to get the mass density of black holes in the universe at that time. And that's what's shown here, okay? So again, time is increasing right to left here. And the y-axis is the mass density of black holes in the universe. So the little points at the left, that's the measured mass density in today's universe. Okay, the black point with error bars is the mass density you get from these early galaxies with the overmassive black holes. And it's only a factor of like 2.5 times smaller than the local density. And that is very, very puzzling, because remember I told you that as these black holes accrete, they produce all of this quasar luminosity, right? That means that if you measure the amount of quasar luminosity you're seeing, then you can figure out how much accretion is happening. And the standard model predicted that the black hole mass density would follow this red line. All right, so the mass density of black holes should be increasing very rapidly, okay, with time. And instead, what these measurements are now suggesting is that the black holes have grown only a very little bit between a billion years after the Big Bang and today, okay, even though we're seeing all of this radiation, and hence there should be all of this accretion. The way to get out of that is it turns out that the this red line is very sensitive to basically how efficiently you're radiating away. Like, okay, so a certain amount of mass falls in your black hole. Some of it gets all the way to the black hole. Some of it is radiated away. And if it's radiated away, then you're not accreting it, so your black hole isn't growing as much. So you can reconcile the black point and the local points if you assume that a lot of the incoming matter is radiated away, okay? That, it turns out, happens if black holes spin very rapidly. But it's weird that that starts happening, but well, it could explain how you get from a billion years ago after the Big Bang to today. But before a billion years, you need to be building up the mass in black holes very, very quickly to get so much more than we expected. So there's like something going on that must be shifting how these black holes are growing quite dramatically. And then there's a second problem, which is how do we again, we believe that the black holes at later times are responsible for slowing down star formation in their galaxies. Well, now we've got these much more powerful black holes at early times, so why aren't they slowing down how the galaxies are growing? Okay, again, there's some tension between what we're seeing early and late that I don't think anybody has any idea how to deal with at this point. All right. I don't want to run out of time, so I don't want to get into this deeply, but I will just mention that if every galaxy has a black hole and that black hole is producing light, then that's another source, another way to get more early bright galaxies that we didn't expect. Okay, so again, these problems all kind of tie together. Okay, and then the last puzzle that I will very quickly mention is this reionization problem. So remember, these galaxies are supposed to ionize grow these little ionized bubbles and fill the universe. And before JWST, we thought that pretty much hung together. Maybe it was actually there weren't enough photons to ionize the universe. Well, if you add up all the things we found from James Webb, there are brighter galaxies, so there's more star formation. Turns out they're producing ionizing photons more efficiently than we expected. You put those things together, and you go from the black line that kind of fits the data to the blue dashed line, okay, which doesn't at all fit the data. It ends reionization far too early compared to our observations. So there's a kind of weird tension there that is unresolved. I'm going to skip some stuff in the interest of time here. But there are other indications, basically based on the spectra of galaxies, that this reionization is more complicated than we thought it was as well. So how are we going to solve this? Okay, well, I have mentioned a couple times that we have spectra of many galaxies. These spectra are exquisite. And with spectra, you can learn a lot more about the physical conditions inside the galaxies. And so hopefully we'll be able to uncover that as we get larger samples and kind of target these questions. Another way to do this is to use other observations, all right? And so one of those that has been exciting for 25 years and will hopefully in the next few years give us some answers is the 21 centimeter line. So this is the hyperfine transition in neutral hydrogen. It produces a photon with a wavelength of 21 centimeters. It's an extraordinarily weak transition, but because before reionization, the entire universe was emitting it, right? We can hope to see it. The challenge turns out to be not so much the raw signal, but the fact that it ends up in a region of the radio spectrum that is contaminated not just by FM radios and digital TV, but by our own galaxy. Our own galaxy is about 10 to 100,000 times brighter than the cosmological signal we're looking for. So there are a number of telescopes that are trying to observe this. This is the Hydrogen Epoch of Reionization Array, with which I'm affiliated. It's a set of 320 dishes in the Karoo Desert in South Africa. We have a few seasons of data. The observers are hard at work trying to analyze it and get rid of all of that contamination and make a measurement. We have some upper limits right now. There should be another paper from us in the next few weeks. that put some limits on what these kinds of galaxies are doing. But hopefully in the next few years, we'll be able to actually make a measurement of how reionization is proceeding. And that will help answer some of these questions about these early galaxies. So right now, we're at a stage where JWST has posed all of these puzzles to us. We don't have clear answers for any of them. But I think in the future, more JWST data, other kinds of data, the 21 centimeter is one example. And then hopefully the theory tools, that the kind of stuff I do to kind of make a physical picture, will help us answer these questions by the end of the decade, or at least shed some light on it. All right. So thank you. And I'm happy to entertain any questions. I do see one question in the chat, which is, do you think that massive black holes were abundant and outside of earlier galaxies or always inside galaxies? So there's a couple of answers to that. We do not know how the first black holes formed, or at least the first supermassive black holes. They could have formed just from stars, normal stars, and then grown rapidly, or there could be some kind of exotic process that is forming them, including sort of relics of physics of the early universe. So there could be black holes forming outside of galaxies, but they're very difficult to see. The black holes inside of galaxies, when the galaxies merge, the black holes could also merge. It turns out that process can give them kicks, like velocities, or accelerate them, okay? And because these early galaxies are so small, the acceleration you get from a black hole merger can actually remove the black hole from the galaxy as well. So there could very well be intergalactic black holes. If there are, they aren't very important because there's not enough material around them to accrete, okay? But there could certainly be a population of them out there. Things like LISA, the Laser Interferometric Space Antenna, hopes to measure the mergers of these early black holes. And so we may learn more about that, a decade or so out from now.
If cosmology is wrong, the mathematical underpinnings there, can that help this problem?
I mean, it very much depends on how cosmology is wrong. So this, I have seen paper. Well, okay, so it's like one of the puzzles right now in cosmology is that if you measure the Hubble constant, the universe expansion rate locally, you get a different answer than if you measure it from the cosmic microwave background. And so there are some models that try to reconcile those by doing weird things with dark energy. Those things can make structure form at different rates, right? And if you can accelerate structure forming faster earlier on, then that will help. Most of the ways, though, that people mess with cosmology, like if you add in a non-standard kind of dark matter, those actually tend to decrease the amount of structure you get at earlier times, so it makes things worse. So yes, there are some scenarios where it is better, but kind of the median crazy cosmology change makes the problem worse.
Thanks a lot for the beautiful talk. I was wondering about the spectrum in JWST. How good is the quality at like redshift 12, 13, and so on? Like, is it possible that, I mean, you don't get a random number for this complex redshift?
Right. So this spectrum this beautiful one that I mentioned from Alice Shapley at UCLA, this is of a galaxy that is toward the end of cosmic dawn. So this is like 1 billion years after the Big Bang. And it's also very, very luminous. If you look at some of these galaxies, let's see. Sorry, okay, here's an example. Oops. These are examples of galaxies that are at redshift of 14. So this is very early in the history of structure formation, and it's a much worse spectrum. And that's largely because this is a very much smaller galaxy at early times. So you see that there's like no light and then this break, and then you can see a continuum, but you can't pick out any lines. So you can't do this kind of careful diagnostics on the very early galaxies. You can really only do that still on the most massive ones. So that's one of the motivations for the next generation of ground-based telescopes. So the biggest telescopes we currently have are about 10-meter diameter on the ground. The Keck telescopes for University of California are an example of that. The next generation people are building will be about 30 meters in diameter. So that's 10 times the collecting area. And that will give you so much sensitivity that you can try to take spectra of these much fainter objects.
Thanks.
Any other thoughts, questions? Hey, let's thank our speaker once again.
Thank you very much.